Welcome back to AERO 1020, the Theory of Flight, presentation number 9 on the boundary layer. In this presentation, we'll discuss the terms relating to the boundary layer and what the boundary layer is. We'll discuss viscosity and define that as well, skin friction, which is a type of drag, laminar flow versus turbulent flow, and the transition region. So what is the boundary layer? The boundary layer is a thin layer of air right next to the surface of an airfoil. It's about 1/10 of an inch wide, and that layer of air shows a reduction in velocity or speed due to the air's viscosity. So what is viscosity? Viscosity is a property of air. Viscosity is the air's resistance to being gradually deformed as it approaches the airfoil. So think of it as the thickness of air. Now, as I said before, skin friction is a type of drag. It's actually technically a type of parasite drag. It's the friction between the surface of the airfoil and the air that moves over it. Boundary layer flow is the thin layer of air that's nearest the surface of the wing, where the flow is altered by friction, skin friction, or viscosity. It's typically, again, 1/10 of an inch in thickness, and the air particles closest to the surface actually come to a complete stop because of that skin friction. As you get further from the surface in the boundary layer, the velocity of the flow starts to increase until it gets to normal velocity. So you can see in this next illustration, as you get further and further from the surface of the airfoil in the boundary layer, the velocity actually increases. The next term is laminar flow. Laminar flow is the smooth flow of air that parallels the wing surface, and it typically occurs from the leading edge back toward the trailing edge of the wing. As you get further and further back from the leading edge of the wing, the size of the laminar flow boundary layer actually increases. The effects of skin friction are also minimized in the laminar flow boundary layer, and you can see in this illustration how the size of the laminar flow boundary layer actually increases as you get further from the leading edge. It's important to note that there are limits to the laminar boundary layer. The smooth laminar flow doesn't hold throughout the entire wing. In other words, the laminar flow starts to transition to a turbulent flow at some point between the leading edge and the trailing edge of the wing. When the engineers design a wing, the ideal is to keep that laminar flow moving as far aft as possible from the leading edge to the trailing edge of the wing. Here are a couple of examples of different airfoils. In the first example, the laminar flow only continues back to 25% of the airfoil. In the second example, you can see the laminar flow extends back to 40% of the airfoil, which is better and closer to the ideal. When the laminar flow boundary layer gets to the transition region, the flow of air can do one of two things. It can either separate from the surface of the wing, which we really don't want to happen because when the flow of air separates from the surface of the wing, we lose lift. The second thing that can happen is it can become turbulent, and turbulent flow is really the lesser of the two evils. So as you can see in this illustration, we start out near the leading edge of the wing with a smooth laminar flow of air. And then we have what's called the transition region. That's the region between the laminar flow and the turbulent boundary layer flow. So what are the characteristics of the turbulent boundary layer? Well, first of all, the air doesn't flow smoothly over the surface of the wing in the turbulent boundary layer. Instead of flowing smoothly, we get whirls called eddies that circulate and move up and down, and the flow of air can also circulate back toward the leading edge of the airfoil. Skin friction drag becomes greater in the turbulent boundary layer, and that's an important point to remember. Again, skin friction drag becomes greater in the turbulent boundary layer. And as the angle of attack is increased, the turbulent flow transition region actually moves forward closer to the leading edge of the wing. In these three examples, you can see an airfoil at different angles of attack. At a low angle of attack, the laminar flow extends almost all the way back to the trailing edge of the wing. And then as the angle of attack is increased toward the critical angle of attack, you can see the turbulent flow starting to form at the trailing edge of the wing, and then moving forward closer to the leading edge until the wing is stalled. So again, to review quickly, as the laminar flow approaches the transition region, the flow of air can do one of two things. It can either separate from the surface of the wing, which we don't want to happen because when the flow of air separates from the surface, we lose lift, or we can get turbulent airflow. Turbulent airflow is not really a bad thing, it's actually a good thing. Turbulent airflow actually tends to draw outside air into the boundary layer, and that kind of energizes the air and keeps it attached to the surface of the wing. And as I said before, we really need to keep the air attached to the surface of the wing to ensure that the wing continues to develop lift. So while the goal in designing a wing is to extend that smooth laminar flow boundary layer as far aft on the wing as possible, the turbulent flow is not necessarily bad in all respects. That's the end of presentation 9 on the boundary layer. The next presentation, number 10, will discuss airfoil design.